So related to our direct comparison test is the limit comparison test. And here we are comparing two series again, just like in the direct comparison test. But the limit comparison test does give us a little bit more guidance in how to choose the series we're going to compare to. And for this, again, like with the direct comparison test, we want to deal with series with non-negative terms. But again, since we're normally checking absolute convergence, that shouldn't be an issue. So we're going to say A sub n is the general term for the series we're looking at, and B sub n is the series we're comparing to. And we always are going to do a limit then, and limit comparison test. Limit is n goes to infinity for the general term of the series we're given to the general term of the series we're comparing to. If that limit is a positive number, then our two series must behave the same way. They either both converge or they both diverge. And that tends to be the most common situation. If, when we do that limit, we get 0, that means B sub n is getting much, much larger on it. And so the only way that our A sub n would converge is if B sub n also converges. But if B sub n were diverging, that doesn't tell us what's happening to A sub n. Or if I do that limit and I get infinity, that means that A sub n is getting much larger than B sub n. So if B sub n diverges, it forces A sub n to. But if B sub n is converging, we don't know what's happening to A sub n. I will admit, when these last two situations occur, I usually will then move on to a different test. For me personally, it's normally the integral test where we find that. But these two situations right here are the direct comparison test. So if you struggle a bit with choosing a series, but you want to do the direct comparison test, these last two situations are actually what the direct comparison test is doing. But it does give you a little bit of guidance for choosing a series to compare it to. Now, the thing that's lovely is if A sub n is our original series, the way we usually choose B sub n is we choose it to be the behavior model of A sub n, which gives us a nice strategy for choosing our bet. And then if we get a positive number, we just have to decide if this series converges or diverges, and then our original series must do the same. So kind of benefits to this, it is usually easier to use than a direct comparison test because we have a strategy for choosing the series to compare to, namely use the end behavior model. Also, this is a really good one to use for when we're dealing with a series that the general term is a rational function. Ratio test works on those, but they tend to be a little tougher on the ratio test, or we end up getting 1 on the ratio test, which remember on a ratio test, if the limit is equal to 1, we're told that's inconclusive and we have to choose a different test. So the limit comparison is a good place to go if the ratio test is inconclusive. So here, if we're saying I want to look at sum n equals 0 to infinity of 1 over m squared, I can't really tell right off the bat right now. So I'm going to go ahead and go to my limit comparison test, namely as a way to an example of it. I could have done my ratio test also, but I'm going to go with limit comparison here. So what that says is I want to compare this to the infinite series of equals 0 to infinity. On top, my first term, the term takes over is 2n. On the bottom, it would be n squared. So this is the same as going from 0 to infinity of 2 over n. Now technically, n couldn't be 0, but we would just say then, well, n starts at 1, because it's whether it converges or diverges as n goes to infinity is what I care about. So I need to see, does this series converge to that? Oops, sorry, I can't make that decision. I need to compare these now with my limit comparison. to see if they're going to behave the same way. So I'm looking at the limit as n goes to infinity. I'm going to do this absolutely, just so I can verify positive or non-negative terms. So my original, 2n plus 1 over the n plus 1 squared, divided by the 2 over n, and evaluating this limit. So that would be the limit as n goes to infinity. I would have infinity over infinity, so I can deal with n behavior models of this, or I could be doing L'Hopital's rule. I'm going to be using n behavior models of this. So on top, 2n squared takes over, and on the bottom, I would have 2n squared also. So this is 1. And what this tells me is that these two series behave the exact same way. So if this series converges, my original series converges. If this series diverges, my original series diverges. And so since I now know they behave the same, I can see, does this converge or diverge? Well, I can see it as a p series because I have a constant over n to the power. Because the power is 1, so I have p is equal to 1. Since p is less than or equal to 1, the series for 2 over n diverges. That's our p-series test. Well, and by the limit comparison, I know that my original series behaves the same way. So my series from n equals 0 to infinity, 2n plus 1 over the quantity of n plus 1 squared also diverges.